All right. So oh, this is fun. Whoops. There we go. Hey, would a kind person care to read the top paragraph?
In the Richard Byron lecture on energy, he uses an analogy to explain the concept of energy and conservation. For each of the items below, describe or explain what energy ideas represented by a term or phrase.
Cool. So what's the house? It must have got cut off there. Rad. That's a good start. So the house is the system.
Where energy is stored, right?
Good. We just call it a system, make it simple. What are the blocks then? So we'll say unit. You said what units of energy? Okay, units of energy, or 1 unit if you prefer. Not a big deal. What are the total 28 blocks? Is it okay? Wait. Hold on. The 28 blocks are the total energy in the universe, total energy in the system. Okay. So total energy, and this is the total energy stored, keyword stored, in system. Everybody good? The blocks that were thrown out the window. Good. Energy transferred out of system. This is good. Yeah, go. Well, we're going to talk about that. We'll get to that. You're awesome. Sound good? The blocks that the neighbor Bruce brought into the house. Okay. Energy transferred into the system. Cool. All right. And the block that was under the rug. Cool. So I'm gonna circle this one. The blocks in the toy box. I'm gonna circle this one. The blocks in the dirty bath. I'm gonna circle this one. Let's just say it this way. Oh, you guys think the mom is what? Everybody agrees there. William, you get it? So this is the physicist or the scientist trying to figure stuff out, right? Is this spelled correctly? No, it's not.
Right scientist.
I'm a right scientist. All right. So the 3 we circled, they're the ones you're unclear on, right? I have a good way. I think I have an idea here. I'm going to just use another analogy to explain an analogy, which makes it really far removed from reality. Money. You got Citibank. They have some of your money. You got Bank of America, Wells Fargo. You got a couple different banks you work with, maybe. You got all these cards in your wallet, checks, maybe, and you use one card. The person the vendor gets paid no matter which card you use. The money has to come from somewhere. But would you agree that your money can be stored in many places?
Yes.
There's 3. We're going to have 3 storage bins for our energy blocks. These are just examples of where they might be. Okay. In our system, are all of these in our system?
Yes.
There's no energy in your bin if there ain't if energy isn't stored in your system, there's no energy in your system, period. Now, these bins are within your system. Make sense? And I could just talk about the accounts now since David brought it up. What did you say again? You said something beautiful. I can't hear you. Okay, what I'm saying is the 3 bins where energy can be stored. You guys agree with the basic idea? We're concerned with where is energy stored, how is it transferred? And you can transfer money from different, you can say, I don't want to work with Citibank anymore, transfer all your money out, right? So you can transfer energy blocks around. You can store energy blocks in specific places, right? But what's the fundamental rule for all of this? It was the last question. In your system? Okay, so all the energy everywhere can't change. If energy leaves, you have to account. So you're an accountant. You're basically an energy accountant. So some folks that didn't do as well in other areas of physics can do quite well here because you're just an accountant. You're accounting for where your energy is stored. You're accounting for how it is moved. That's all. And that's all we do. Does this make sense? So these are just different storage accounts. And the 3 you're going to be using, one was already mentioned. David, what would you say again? So it's not a transfer of energy from one place to another. It's a storage bin. And energy we say energy is stored in kinetic energy if your system is doing what? Kinetic. What does it mean? There you go. So, and let me ask you this. You can use your sensory apparatus to decide if there's a lot of energy or little energy. Ready? If you're scared, use scariness factor. If you're scared, there's probably more energy. Okay? Would you rather get hit by this small thing moving 1 meter per second or 100 meters per second? Which has more, if this is your system, which has more kinetic energy stored in it? You guys good? Now I can also add to that the same object. No, sorry, my bad. The same speed. Both objects moving 1 meter per second. You with me? One object has a much greater mass, which is worse. So energy stored in something's motion, energy stored in the kinetic energy bin. You have more energy stored in that bin when there's more mass, when there's more speed. Make sense so far? Second bin, thankfully I wore glasses today. So if I do this, okay, which do you think is worse? This? This. Again, this rubber band is my system. So if there are molecules in your system that have elastic properties, like a rubber band or spring, and those molecules are stretched, or springs, you can also compress them. So if the molecules are stretched or compressed, and they can store energy, you guys good? We say that's the elastic energy bin. Cool? And then the most confusing one, I should probably draw a picture. Let me draw a picture of Earth. This is a cute picture. There we go. So here's what I got. Here's a very nice picture of the Earth. Ready? There. Good? Okay. Now let's say you're located on the Earth's surface. You're located here. What's the gravity field strength, everybody? Okay, so I'm just going to call it 10 newtons per kilogram. Is everybody good there? And I'm going to draw cute little arrows to show the direction of my gravity field. So when humans can't actually see something, they make up ways of understanding it. And that's what a gravity field really is. It's a way of understanding what would happen to an object if it were in this gravity field. It would go in the direction of these arrows, and the length of this arrow means a stronger gravity field. So a bigger acceleration due to gravity. You guys get it? Okay. If I go further out, what's going to happen to the length of these arrows? Same direction? So out where the moon is, I think our calculations in the past showed 0.03 meters per second squared. Was that what we got? It was a really small number. So out where the Earth's moon is, anything located within that sphere, because this is a three-dimensional sphere, so I can't really draw it. But there's this three-dimensional sphere, and everywhere along the surface of that sphere, you're talking about 0.03 meters per second squared, or 0.03 newtons per kilogram gravity field strength. If you go closer to the center, what's going to happen to the gravity field strength? Okay? So I'm trying to get you just to visualize what I mean by gravity field. Okay? And you're not, so the closer you get to the center, the longer these arrows, but their directions are essentially the same. They're towards the center. Everybody good? It's just the idea. So when we say energy stored in a gravity field, what we mean is if I take something, if I drop it from here, it's not that bad, right? Won't hurt me that much. But I lift it. If its position changes with respect to the gravity field it's in, then as I lift it, is the fear factor getting less or more? I'm pretending to be scared, but I'm not really scared because I know I'm not going to drop it on my head. But as something gets higher and higher and it's about to fall on you, you're more scared. So there is more energy stored where? Not just the object. If I had just this object alone without a gravity field, would it be so scary? So this system has to include my object and the gravity field it's in, or it's not scary. It's not storing energy. You with me? No gravity field, no energy stored in gravity field. So we need a system that includes a gravity field for us to have gravitational potential energy. Those are the official words we use. So we got 3 storage bins: gravitational potential energy, kinetic energy. What's the third one? Everybody good? Energy stored 3 possible places. Now, in nature, do you think there's just 3 places? But within the scope of this class, that will be enough. Okay? So your life will be simple in that way. We have three storage bins to worry about in this class. And we have ways we can transfer energy too. You know the example of the block being thrown out. That's energy going out of your system. There's energy going into your system. So first, why don't I go straight to an example? I think that'll help you the most. Based on this lecture so far, what do you think it means to say energy is conserved? How could I say this? Okay. Well, talk about a system. You can't really talk about energy, you notice, without talking about a system. So how could you speak in terms of a system here? I'll start. E total in system. Yes. A block. Go ahead.
E total in system is equal to energy removed from system.
Okay, I'm going to write in the beginning or initially. Okay, I think I see where you're going now. Okay, go ahead.
Is equal to energy removed from system.
Okay. You mind if I do it this way? Minus E lost. See what I'm doing? Plus, what am I going to write here? E gained equals, is it necessarily going to equal 0?
No.
Okay, so the E total in system at the end. Are you guys cool? These two, I'm talking about energy that's transferring, right? Everybody good? This one, I'm talking about E stored energy. Whoops, my bad. So energy stored initial. And this is what? So the ones in black, what are the three possibilities we just talked about? I don't hear you guys. Okay, I'm hearing you now. How about everybody? E, give me one of them. E kinetic. You guys mind if I use these symbols? Make life easier. E kinetic for energy stored in your motion of your system. What else? Okay. E elastic. What else could it be? What? Gravitational potential. How about we just call it EG? Everybody good? So these on this side is the same all over again. The same three. Okay? So I'll clone them and I'll put them over here. Are you guys cool with the idea so far? Okay? You don't have to write any of this down because I'll just put a post on the website for you. Just try to understand it. Okay. So I need someone to read this. Because by example, it's gonna start to make sense. Go ahead. Very cool. So I'm going to choose moments in time very carefully. I've got a box sliding down a hill, reaching a flat part. Okay? The first moment in time, since we're concerned with our our kinetic energy storage bin, what can you say about the velocity at this moment in time? When the block is just released. Would you say that velocity is 0 at this moment? That would be very convenient because then our kinetic energy bin is empty. You with me? So what can you say about the height? I'm talking about this measurement. What can you tell me about that height? Maximum or minimum? Thus, our gravitational potential energy is maximum. You see how it works? You must choose your moments in time very wisely. Okay? So this is H, and H is maximum. Everybody good? This is the first worksheet is this one. There's 3 problems, and I'm probably going to do one example now. You can have it as it'll be on a video, and the notes will be online. What? It'll be on your website, and yes. And then the other 2 problems you'll do tonight for practice and try to get comfortable. Okay? So let's choose our system. I probably should have done this first. What's your system going to be? I'm drawing a circle, and I'm going to put whatever my system is inside that. Box. What else? Okay, you're talking about what exactly? Not just the word gravity. If we didn't have a gravity field, would we have any EG? So we're including gravity field. You guys good? You can write GF for gravity field. Okay? In the end, where do you want the block to be? Read the situation. It doesn't have to be the end of this story here. It can be any convenient moment in time. What's the next convenient moment? Okay, a couple people at once. Rachel, go, and then John. Okay, this is our system. We're choosing our box and our gravity field. You see why? Well, that's a storage bin. We'll get to that. We'll talk about that in a moment. But is the box moving? Thus, we say there's energy stored in the system in the kinetic energy bin because the box is moving, because our system is moving. Does that help? Okay. We'll do that part in a moment. Now, what's going to be the next interesting moment in time? That's a good one. Why? What's happened to our height? Maximum or minimum? So a lot of energy problems work this way, where our height is minimum. Okay, what can you tell me about the velocity? Okay, so would you folks agree that V is max? Everybody good? No, I'm saying that the velocity, let's say this is a smoother curve here, so it doesn't just like clunk, you know,
Okay.
like a roller coaster or something. You guys good? Okay, so this is at maximum velocity. So I'm asking you to envision moments in time that are extremely useful for us. The first is when the velocity is 0, next when velocity is maximum, and I got this just from these words. So you'll have to do that on your own. Then I got maximum height, minimum height. Okay, so let's account for our energy stored. What are the 3 places we've got in this class? Where can we store our energy? Okay, E elastic is a possibility. What else? E kinetic. Okay, so EG. Okay, and I can have this energy stored in the beginning. I can have this energy stored in the end. So I'm going to clone this sucker. Got him? Okay, move him over here. This is energy stored in the beginning, energy stored in the end. Everybody good? Okay, so, is there a spring even in our system or elastic molecules?
No.
So this one, before we start, is done. I'm just going to do that. I'm going to say it's 0. So I'll write numbers down here. Now, is the object moving yet?
No.
This moment. So it's not moving. So our kinetic energy bin, our elastic energy bin are both empty. You guys good? 0 plus 0. What about EG? Let's make up a simple number. Because now I want you just to make up numbers. We're not going to use any equations until you're comfortable with the concept. Okay? So I'm going to make up a really difficult number like 4. Okay? And I drew 4 blocks to represent that. And now I have plus 4. Everybody good? Okay. Any spring to worry about?
No.
Okay. What happened to our EG?
0.
Now notice something. He immediately called it 0. Are we at sea level? Are we at 0 height?
No.
Can we call energy 0?
No.
Yeah, we can. If we called this 10, it doesn't change anything. It just makes our equation stupid and complicated. Calling this 0, calling our lowest height 0.
As long as the height stop changing.
If the height were lower than this in the next stage,
Wait a second.
like if there was another hill, that wouldn't be so good. But if this is our lowest height, this actually makes a lot of sense, and it simplifies our equation. You guys cool? Well-
because then if that wasn't 0, then we have to proof it on the other side too.
Okay, think of it this way. Anywhere we conduct our experiment, are we going to have 0 gravity field? We're going to be on the surface of the Earth. Gravity field is going to be 10 newtons per kilogram, right? So just because we have a gravity field, does that mean we have to make the energy, is energy and gravity field the same thing? Good. So what I'm saying is whatever your lowest height is, why not call that your 0 energy? You're not calling it 0 gravity field. You're just calling it 0 energy.
Yeah.
You guys dig?
Yeah.
They're not the same thing. So you don't have to worry about the fact that the Earth's still pulling or there's still gravity field. Who cares? We're saying it's 0 energy relative to where we started. Cool?
Yeah.
Okay. So what can you tell me about EK?
It's maximum.
Okay, you guys really want to say 4? I'm suggesting now that not all of these 4 blocks that were in the gravity field, they were stored in the gravity field box system, not all 4 of those blocks are going to make it to EK. Why? Why don't they all make it? Give you a hint. Here's your hint. You're sliding on a surface that's rough, right? So how do we account for this? You remember the block that flew out the window? That's what this is. You have a block leaving your system. And we call this energy dissipated. We're just accounting for it. That's all we're doing. So we got energy dissipated. So I'm going to make it in red because we're not talking about a storage bin. It probably makes more sense to think of this as an energy that's being transferred, right? A transferring of energy out of your bin to somewhere else. Make sense?
So how do you know that a block is going to be?
I made it up. The fact that it's one block does not matter. The concept that we always lose, that we're losing something, that not all the energy that's stored in gravity field box system is going to make it to EK, that's the fundamental principle. Whether it's one block or two or three, who cares? And later we'll have equations, but we don't have equations for that one. So you figure out everything else to figure out that one. You get what I'm saying? You won't know an equation for that. Well, we have approximations, but we don't have a good equation for it.
For EK, is that necessarily the velocity? Like,
Well, would you rather use the scariness factor? Would you rather get hit by a baseball or a bowling ball going the same speed? So is mass important?
yes.
Now, would you rather get hit by a baseball that is tossed by your 3-year-old or thrown by a professional baseball league pitcher, full speed? So two things are important. What are they? Now, as far as the actual equation, we're going to have to use our equipment to figure that out. Because it's not quite that simple. But this is just to start you off with the idea. You get it?
Because like when you write down for EK, I just put it like,
We're making up numbers right now. We're making up blocks. We're literally playing Feynman's game with blocks. Okay? So can I, for symbols, I'm going to make the energy transferred in red. I'm going to say minus E dis equals. Now, now can you help me? Like, I'm going to draw this block below because I'm subtracting it. How many am I left with now?
3.
Does our equation make sense?
Yes.
That's what we're concerned with at this point. And that would be your last check. Does 4 minus 1, actually I should be consistent, make it red. Does 4 minus 1 equal to 0 plus 3 plus 3? Yeah, 4 minus 1 is 3. You guys get it?
Yes.
And this is what you'll do. I'm not done with the problem though. I've separated into 2 stages, but I'm going to have to go from this stage to the end when the block stops. So I'm going to copy all of this down here. You guys cool? And it's just the same thing again. And the 3 problems you got your, I don't know how many stages you're going to want, how many states, how many moments in time. You figure that out. It's good for you. Okay? It's the best way for you to learn this stuff. Okay, we had the block here. It was at V max. It was at H min, right? Our system was box and gravity field, right? And at some later time, the box stops, so velocity is 0. H is still min. Is everybody good? And we had 3 blocks in the EK, the EK account. So we had nothing in elastic, obviously. We had nothing in EG, obviously. So these are both 0. But we had some EK, right? We had 3 blocks EK. And I'm going to draw 3 blocks here. Are you guys cool? Everybody good? I drew them above because they're added to our system. They're in our system. Okay? Now, in the end, EG, 0, right? Still, didn't change. EK, see, now you start to see that if this wasn't 0, did it change?
No, so it doesn't matter.
So who cares? Do you dig what energy is all about? It's about how energy is transferred and where is it stored. It's not about absolute how many blocks necessarily. It's about, did the EG change from here to here? It didn't. So it might as well be 0. And then we got was our last one? Okay, and that we didn't have to worry about the whole in any of this problem. Okay, what happened? How? Okay, and we're accounting for this with the energy dissipated account, and energy dissipated is a complicated one that we don't really understand, but could I say that this energy would be hard to transfer back to EG or EK, or E elastic for that matter? Would it be hard to get back into our system? Okay. This E dis you're calling friction. Where is the energy really? What is friction? Rub your hands together. What happens? Okay, what is friction?
Heat energy.
So molecules are doing what? So I ask again, how are we going to retrieve this energy stored in molecular motion? Yeah, I'll ask again. How do we retrieve energy stored in molecular motion? It's not lost in terms of the universe, but in terms of us retrieving this E dis and putting it back into EG, E elastic, EK, is that going to happen? I'm not saying you can't lift the block back up, but that's different. That's energy that comes from you, the food you ate. You guys dig? So how many blocks? Try that again. How many blocks?
3.
Okay. This thing, most people sort of like energy, especially at this level. Now, does our equation make sense? I need 3 down here. So I do -3 equals what? We good? Everybody cool here? So that was number 1. Which ones are you doing?
2 and 3.
Sound good? We whiteboard them tomorrow, see where you're at. If you're comfortable with 2 and 3, by all means, the worksheet's already up. It's called, I think it's the next one, called Energy Storage and Transfer. All of them, yes. And let me go back to your website. If I scroll down, it's where is energy stored. So this one here is just more practice. It's the same idea. There might be, you know what, we made it really easy. You see how we labeled the moments in time that are useful? Actually, some of these moments in time aren't that useful, but yeah. I mean, it's just more practice. So the focus is where is energy stored and how is it transferring? Cool, banana? If you do finish 2 and 3, by all means, work on this one too, because we may actually whiteboard it tomorrow. It's possible. Rachel, do you have a question? You good? Go, David. Yeah, let me show you. This is called an energy flow diagram. I got a little crazy on the beginning of the energy flow diagrams worksheet. We just did 1 out of 3. Okay, it also says do a system schema. You don't have to do that. It's not a bad thing to do though, so I shouldn't say you don't have to do that. It's good for you. It's not part of your energy flow diagram. It's nice to give you a sense of the interactions. Make sense? And choosing your system. Do you think this is the only way to do this problem? Let me just point something out really quick. Another way to do this problem, I'm not recommending any particular way, but if we added the surface to our system, what would happen to ES? That energy wouldn't be leaving our system. So EDIS would have to be a storage bin then. And that's not wrong. It's a little weird, but it's not wrong. You guys cool?
Basically moving all the energy from there into one giant bit.
Yeah, and in this unit, you're accounting for the energy. You're looking at where is it stored, how is it transferring. That's all. And you'll be amazed at what you can do. I should probably say this now. You remember all the kinematics problems we've done?
Yes.
You can solve those and problems we haven't been able to do using energy. That's how powerful it is. It's kind of mind-blowing.